Hey there guys, this one is the 2019 Edexcel A-Level Maths Paper 3-1, which is the statistics part of Paper 3. Let's go. 3 bags A, B and C each contain 1 red marble and some green marbles. Bag A has 1 red, 9 green. B has 1 red, 4 green, and C has 1 red, 2 green. Sasha selects the marble at random from bag A. If it's red, he stops. If it's green, he selects the marble at random from B. If it's red, he stops. If it's green, he selects the marble from bag C. Part A. Draw a probability tree diagram to represent this info. Alright, so hopefully there's nothing too tricky there. So our tree diagram will look like that. Part B says to calculate the probability. Sasha will select 3 green marbles. Okay, so let's call that the probability of green, green, green. So that is 9/10 times 4/5 times 2/3. Okay, now that is 72 out of 150. So that can cancel to 12/25, or as a decimal, it's 0.48. Cool. Let's see. Find the probability Sasha selects at least 1 marble of each colour. Alright, so this is one of those times where it's easier to find what we don't want. So we're going to do 1 minus. Now we don't want him to get a red from bag A, so we're minusing the probability of red. And we don't want him to get green, green, green. So that is 1 minus 1/10, or 0.1, minus 0.48. So that is going to give us 0.42. Given that Sasha selects a red marble, find the probability he selected it from bag B. Alright, so we want then the probability of bag B given red. Alright, so in part C, I used the probability of R as the probability he got a red from bag A. Now I'm going to be using the probability of R as the total probability he gets a red. So, the probability then of B given red is the intersection. So, the probability of B and red over the total probability of getting a red. Alright, so that then, for him to have gotten a red from bag B, he would have needed to get a green from A and then a red from B. So the top is 9/10 times 1/5. Okay, now on the bottom, the total probability of him getting a red is 1/10 from bag A and then a green from A and a red from B, so add 9/10 times 1/5 and then green from A, green from B and a red from C, so 9/10 times 4/5 times 1/3. Alright, so up on top we have 9/50 and on the bottom we should get 13/25. Alright, so 9/50 divided by 13/25 is 9/50 times 25 over 13. So we have a common factor of 25, so we've got 9/2 times 1/13, so it's 9/26. Number 2. The partially completed box plot shows the distribution of daily mean air temperature for the data from the large data set for Beijing in 2015. An outlier is defined as a value more than 1.5 times the interquartile range below Q1 and above Q3. The three lowest temperatures were 7.6, 8.1 and 9.1 degrees Celsius, and the highest was 32.5. Partey wants us to complete the box plot, clearly showing any outliers. Alright, so we need to work out the interquartile range, so we can see that Q1 is 19.4 and Q3 is 26.6. So the interquartile range is 7.2. Which means that 1.5 times the IQR is 10.8. Alright, so now let's check the lower values. So 19.4 minus 10.8 is 8.6. So that tells us that the 7.6 and 8.1 were outliers. Alright, well then let's do the upper. So 26.6 add 10.8. And that is going to give us 37.4. So the highest recorded value, 32.5, is not an outlier. Alright, so now we need to complete the box plot. The outliers are plotted as crosses. And you should get something that looks like this. B. Using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. Alright, so I will link the data set down below. So here it is for Beijing. Now the data starts in May and goes all the way down to October. Now, if we look at temperatures, October is the coldest month, so we would suggest October. Next up, Simon produced these summary statistics for the daily mean air temperature in Beijing for 2015, Part C. Show that to 3 sig figs. The standard deviation is 5.19 degrees Celsius. So, we're given the formula that we need. So here, sigma is root SXX over N. So that's root 4952.906 over 184. Which does indeed to 3 sig figs give us 5.19. and decides to model the air temperatures with a random variable T, which follows a normal distribution with a mean 22.6 and a variance 5.19 squared. Using the model, calculate the 10th to 90th int percentile range. Alright, so this is how then things are looking. So there are these two values, T1 and T2. So we want the probability to the left of T1 to be 0.1 and to the left of T2 to be 0.9. So if probability T is less than T1, is 0.1. Now, on your calculator, you want the inverse normal function, put in the area as 0.1, mu 22.6 and sigma 5.19. Press equals and we get 15.94. Okay, and then do the same for T2. So we want that probability to be 0.9. Now that gives us that T2 is 29.25. Alright, so what we now want is T2 minus T1. Which gives us 13.31 degrees Celsius. And want to model another variable from the large data set with a normal distribution. We want to state two variables that would not be suitable, giving a reason for each. Alright, so first up then, if we look at rainfall, we can see that it has a lot of zeros. Now, what that's going to do is skew the data and make it non-symmetrical. So we can't use rainfall, and the other one is wind speed with a Beaufort conversion, because that's in words, not numbers. Or, to be posh, we can say it's qualitative and not quantitative. Number 3. Barbara is investigating the relationship between average income, GDP per capita, ex US dollars, and average annual CO2 emissions, Y tons, for different countries. She takes a random sample of 24 countries and calculates the PMC as 0.446 per day. Stating your hypotheses clearly, test at the 5% level whether the PMC is greater than 0 for all countries. Alright, so H0 is going to be that the PMC is 0. Now, for the PMC, we usually use a row, which is like P. So, row is equal to 0. And H1 is that row is greater than 0. Alright, so what we now need to find is the critical value from Spearman's rank. So, this is page 37 in the formula booklet. So we want 5%, and then we want n as 24. So we get 0.3443. Now, her value 0.446 is greater than the critical value. So that means there is evidence that PMC is greater than 0 for all countries. Borough believes a non-linear model would be a better fit for the data. She codes the data using M is log 10x and C is log 10y and obtains the model. C is minus 1.82 at 0.89 m. She calculates the PMC for this and gets 0.882. Part B. Explain how this value supports Barbara's belief. So, 0.882 is greater than 0.446. Now, the closer the PMC is to 1, the stronger the correlation. So, here, this shows stronger correlation. Part C. Show that the relationship between y and x can be written in the form y is ax to the n, where a and n are constants to be found. Alright, so we know that log y is minus 1.82 at 0.89 log x. So the log written with our base is log base 10. So on the log x, the 0.89 can be written as the power of x. So we have log y is minus 1.82 plus log x to the 0.89. Okay, now we are going to subtract log x to the 0.89. Okay, now on the left, that combines to log y over x to the 0.89. Okay, next, to get rid of the log, we raise both sides as a power of 10. So we get y over x to the 0.89 is 10 to the minus 1.82. Okay, now multiply through by x to the 0.89 and we get y is 0.0151 x to the 0.89. Number 4. So Magali is studying the mean total cloud cover measured in octaves for Luchars in 1987 using data from the large data set. We have the data for all 184 days in the table. Per day, given that one day is chosen at random, calculate the probability it had a cloud cover of 6 or more. So all that we need to do there is add 52, 52 and 28. So that is 104, 124, 132 out of 184. Gali is investigating whether the mean daily cloud cover can be modelled using a binomial distribution. She uses the random variable x to denote the mean daily cloud cover and believes x is binomially distributed with n as 8 and p as 0.76. Using this model, find the probability x is greater than or equal to 6. So, the probability that x is greater than or equal to 6 is 1 minus probability x is less than or equal to 5. So, for less than or equal to 5, we should get 0.297, which gives us an answer of 0.703. To find to one decimal place the expected number of days from a sample of 184 days with a mean cloud cover of 7. Alright, so we need to find probability that x is equal to 7 and then multiply that by 184. Alright, so for that probability you want binomial PD, and we should get 0.281. Now, to one decimal place, that is 51.7. Part C, explain whether your values from Part B support the use of Magali's model. So, we are going to compare results from the model to the recorded data. So, from Part A, probability x is greater than or equal to 6 was 132 out of 184, which is 0.717. Using the model, we got 0.703, which is very, very close. So that's all good. And then, using the model, for the number of days we would expect to have a cloud cover of 7, we got 51.7, and in the table, 7 was 52 days, which again is very, very close. So, yes, our values from B do support the use of the model because they match up very closely with the recorded data. There were 28 days in Lucia's with a mean total daily cloud cover of 8. The table shows the mean daily cloud cover for the following day from each of these 28 days. Part D wants us to find the proportion of these 28 days that had a mean total daily cloud cover of 6 or more. Alright, so again, that's easy. That's just 5 add 9 add 9 out of 28. So that's 23 out of 28. Final part, comment on the use of Magali's model in light of the answer to part D. So, to use a binomial distribution, events must be independent. Now, we can see from this table, remember, they all had a cloud cover of 8 the previous day, Now we can see that a very high proportion of these had, again, a high cloud coverage. So that suggests that cloud cover from day to day is not independent, which means a binomial model would maybe not be valid. Number 5. A machine puts liquid into bottles of perfume. The amount of liquid in each bottle, d milliliters, follows a normal distribution with a mean of 25 ml. Given that 15% of bottles contain less than 24.63 ml per day, find to 2 decimal places the value of k, so that the probability d is between 24.63 and k is 0.45. Alright, so the distribution then is going to look like this. Now, we know to the left of 24.63, we have 0.15. Now, between there and the mean, we then have 0.35. So, between the mean and k, we have 0.1. Alright, now, the way that I'm going to do this is I'm going to be using the inverse normal on the calculator. So, what we need to do to find k is find the standard deviation. So, we're going to say that if we standardize this, and then z follows the normal with a mean 0 and variance 1. And here we're not dealing with a sample, it's population, so z is x bar minus mu over sigma. Alright, so when probability that d is less than 24.63, we know that is 0.15. Alright, now we can find the corresponding z value. So find inverse normal on your calculator. The area is 0.15, mu is 0, sigma is 1. And we get z is minus 1.04. So, from that, we can get that x bar minus mu is 24.63 minus 25. Over sigma is minus 1.04. So, from that then, we can get sigma is minus 0.37 over minus 1.04, and that gives us sigma as 0.356. Alright, so now we're going to do the same thing at k. So, we know that the probability that d is less than k is 0.6. So, we can get the z value for that. So, for that, we are going to get z as 0.253. So, here then, we then know in that k minus 25 over sigma 0.356 is equal to 0.253. So, if we then multiply through, we get that k minus 25 is 0.094. So, k to 2 decimal places is 25.09. Okay, now a random sample of 200 bottles is taken. Using a normal approximation, find the probability that fewer than half of the bottles contain between 24.63 and k milliliters. Alright, so we know then the probability that d is between 24.63 and 25.09 is 0.45. Now, we can use a binomial distribution. Bottles either do or do not contain an amount of liquid between these two values. So we would need to use a different letter. So let's say x is binomially distributed n is 200 and p is 0.45. Now, to then get a normal approximation, we now need to find the mean and variance of this binomial distribution. So the mean is NP, which is 90, and the variance is NP times 1 minus P. So 90 times 0.55 is 49.5. Alright, so now we can set up a normal distribution using these two values. So we again have to use another letter, so let's use y. So mu is 90 and our variance is 49.5. Okay, now what we're trying to work out is the probability x is less than 100. But we want to use the normal approximation. So this is approximately probability. Well, remember that a normal distribution is continuous. So we want probability y is less than 99.5. Because 99.5 and above would round up to 100. Okay, now for that you want normal CD, lower as 0, upper as 99.5, sigma as root 49.5, and mu as 90, and we will get 0.912. Now the final part, the machine is adjusted so that the standard deviation is now 0.16. Hannah now believes the mean amount of perfume in each bottle is less than 25 ml. She takes a random sample of 20 bottles and finds the mean to be 24.94 ml. But C. Test Anna's belief at 5% level. State your hypotheses clearly. Alright, so H naught is going to be that mu is 25. Her belief is that mu is now less than 25, so H1 is that mu is less than 25. Alright, now we know then that under H naught, and because we're now talking about a sample mean, we should say that under H naught D bar follows a normal distribution. Now mu is 25 and our variance is 0.16 squared over 20. Now, what we want to calculate is the probability that D bar was less than 24.94. So again, we want a normal CD, lower as 0, upper as 24.94, mu as 25, and sigma as 0.16 over root 20. And we will get 0.0468. Now, that is less than 0.05, which means under H naught it was less than 5% likely she would have got D bar as 24.94. So this tells us to reject H naught and then finish with a closing statement saying something along the lines of there is significant evidence to support Hannah's belief. Okay then guys, that thankfully is the end of the statistics. So next up it's the mechanics. I really hope this has helped. Good luck in your exams. Take it easy. Take care.